Trucks deliver waste cardboard, paper, plastic, wood, certain metals and so forth from industrial and municipal collection streams to sorting centres, where we weigh, store and feed them into the sorting line. Certain types of waste, for example waste electrical and electronic equipment, follow specific treatment circuits. First, we separate waste by size in a trommel screen, which is basically a spinning drum. The large and small waste is sifted out, then treated. Then most of the waste reaches the next screen, which separates it according to its density and shape. The flat waste heads up, and heavier hollow waste heads down. An overband magnetic separator lifts all the waste that contains iron. An optical sorting head then separates waste according to its material. Here, a scanner analyzes the waste that travels through its light beam, and compressed air blasts eject the waste that contains the material we want to extract. Then, several optical sorting heads separate the other types of waste, different types of plastic for instance. We use our self-adapting sequential sorting system instead of a full battery of sorting heads. This machine sorts waste in loops, according to the predominant material that the scanner detects on the belt. Operators then check the automatic sorting. They use innovative remote sorting capabilities to eject unwanted materials simply by tapping a touchscreen. The sorted materials are compacted into bales and inspected carefully for tracking purposes. Manufacturers can then use them as raw materials to make new materials or new products, which will be used, reused and recycled again and again.
Once trucks arrive, they are weighed and checked in before heading inside to the tipping hall. The waste is unloaded onto the tipping floor and visually inspected for any unacceptable items, which are removed for separate recycling or proper disposal. Waste is then pushed into a storage pit and thoroughly mixed before being loaded into bins, which we call hoppers, where it travels to the combustion chamber. The tipping and waste storage areas are maintained under negative air pressure to contain dust and odors. Once fed into the combustion chamber, waste is combusted at extremely high temperatures in a self-sustaining process at approximately 2,000 degrees Fahrenheit. A typical hopper load is completely combusted in 1 to 2 hours. As waste is burned, the heat converts water in the steel tube-lined walls into steam that rises through boiler tubes where it is superheated. The steam turns a turbine-driven generator to produce electricity, or may sometimes be used directly for heating or industrial processes. The electricity produced by the turbine generator is exported to local utilities for use in homes and businesses. Each ton of waste can generate 550 to 700 kilowatt hours of electricity. Steam from the process is condensed back into water and returned to the boiler tubes, making it an efficient, closed-loop system. After combustion, the volume of waste is reduced by 90%, leaving an inert ash and metal. Remaining ash is beneficially reused or landfilled as non-hazardous waste. Ferrous metals such as iron and steel are recovered using a rotating drum magnet, and non-ferrous metals like aluminum and copper are separated by an eddy current system. Collected metal is sold to be made into new products. State-of-the-art air pollution control equipment ensures that emissions are well below limits to be fully protective of human health and the environment. We neutralize acid gases using lime in a scrubber reactor and inject activated carbon for heavy metal control. We control emissions of particulate matter primarily through a bag house, which employs thousands of fabric filter bags. All flue gas must pass through the bags before exiting through the stack. Throughout this process, the control room closely monitors emissions through a real-time continuous emission monitoring system, controls steam flow, and a number of other automated systems inside the facility.
Every day, tankers arrive and deliver byproduct, which is pumped into a reception tank and then a digester, where it stays for around 40 days, monitored all the while by a team of lab engineers on site. In the digester, microorganisms break down the byproduct into methane-rich biogas. This process is called anaerobic digestion, and it works in the same way that the body burns calories for energy, but on a much larger scale. The process captures a biogas, which consists of 60 to 65% methane, that is ideal for renewable energy production by fueling a 500 kilowatt biogas combined heat and power engine. This provides electricity and heat for the plant, and surplus electricity is exported to the national grid. Biogas is cleaned and upgraded to almost 100% pure methane, suitable for injection into the gas grid. Nothing for waste. After digestion, the byproduct is pasteurized at 70 degrees C for 1 hour, with leftover digestate returned to land as nutrient-rich fertilizer.
Household and industrial waste that is not recycled or recovered elsewhere is brought to the landfill site by truck. The waste is weighed and checked to make sure it is not dangerous in any way. It is then taken to a landfill cell. The design and location of these cells are thoroughly studied beforehand to make sure the environment is protected. Depending on the nature of the ground, the base and sides of each cell may be reinforced with an impermeable mineral layer. Then the cell is lined with watertight membranes to keep the waste mass contained. Waste is deposited in a cell in operation, then spread out and compacted. This operation is repeated, so the layers become increasingly dense as they accumulate. The rainwater that percolates through the waste forms a liquid known as leachate, which is drained off and treated. After a cell is filled to capacity, it is closed and covered with a layer of soil that is planted to ensure the site blends into its natural surroundings. The cell's environmental impact is monitored for several decades. Inside the airtight cell, an absence of oxygen causes the organic waste materials to ferment, a natural process that creates a large buildup of biogas, made up of a mixture of methane, carbon dioxide, nitrogen and oxygen. This biogas is captured by a network of vertical and horizontal wells that crisscross the layers of waste. It can then be used in a local industrial process or conveyed to a cogeneration plant. Next, the biogas is purified before being burned to fuel combustion engines. The combustion heat pushes a set of pistons, which in turn drive an alternator. This alternator produces electricity. Some is used on site and the rest is delivered to the high-voltage national grid. Residual heat from combustion can be transferred by heat exchanger to a nearby district heating network or to an industrial or agricultural facility. Capturing and utilizing biogas from landfill waste means less methane is released into the atmosphere, so it contributes to combating climate change as well as preserving resources. District heating replaces individual boilers. It uses less energy, costs less, is environment friendlier, and makes cities more pleasant places. Here's how and why at a glance. We generate the heat in boilers fueled by a variety of sources of energy. Most of them are renewable, biomass for example. And we also reclaim heat from waste incineration. That heat travels as hot water or steam through an underground pipe system. This is the primary circuit. Then it reaches substations in apartment buildings, office blocks, public buildings, and sometimes industrial districts or retail areas. Each substation has a heat exchanger that transfers the heat from the primary circuit to the secondary circuits in buildings. Inside, they split into heating circuits and hot water circuits. The heat then warms up the building, through underfloor systems and radiators for instance, and other appliances. The heating in these buildings is reliable, clean, quiet, and saves money. Once the water in the primary circuit has warmed up the building and cooled down, it returns to the heating plant, where we warm it up again. District heating systems combine renewable energies and digital technology to help to improve energy efficiency in cities and to make energy management smarter.